Hey, welcome back. In this video, we're going to continue discussing decrease and conquer, but we're going to focus on decrease and conquer applied to 0-1 matrices. So we talked about 0-1 matrices a little bit before, and we went over a bunch of definitions related to extremal functions of forbidden 0-1 matrices, and we proved some properties of these extremal functions, and we looked at some operations that preserve the order of the extremal functions. So I wanted to briefly review some of the definitions for 0-1 matrices, and then to discuss how decrease and conquer can be applied to 0-1 matrices and their extremal functions. So first, to review, a 0-1 matrix, it's just a matrix where all the entries are equal to 0 or 1. So you've probably seen these before. If you've taken linear algebra, you've definitely seen this one plenty. So that's an identity matrix. And when we write an M by N matrix, we mean a matrix that has M rows and N columns. So this one over here is a 3 by 3. And here's this terminology that we introduced in the last video. A 0-1 matrix A contains a 0-1 matrix B if some submatrix of A either equals B or can be turned into B by changing some ones to zeros. So, for example, if this is our A and we have some B here, and some C here, and let's say we also have this D. So A contains B. So this submatrix right here, which has the first 2 rows and first 2 columns, the intersection of the first 2 rows and first 2 columns, that gives us a copy of B. So that submatrix equals B. So A contains B. A also contains D, because we can take that submatrix and we can turn this 1 to a 0 if we want, and that gives us a copy of D. So it contains B and D. However, we can look at all of the 2 by 2 submatrices of A, and we'll never be able to have the top right and the bottom left both be 1s in any 2 by 2 submatrix. So it does not contain C. And we define this extremal function based on avoidance. Avoidance is just the opposite of containment. So if A does not contain B, we say A avoids B. So A, in this example, avoids C. And given this definition of avoidance, it's natural to define this extremal function. Given some forbidden 0-1 matrix P, it's forbidden, so we're trying to avoid it. We define the extremal function EX of NP to be the maximum possible number of 1s in any M by N 0-1 matrix that avoids P. There's also a version of this definition for M by N matrices that are not necessarily square. So there's a version we talked about in the last video on 0-1 matrices, EX M N P. This version, we allow the matrix that's avoiding the pattern to have dimensions n by n instead of requiring it to be a square n by n. But otherwise, the definition is the same. And in this video for today, we're going to focus just on the square version of the extremal function. Most of the results that we'll see, we could generalize to the non-square version, but the square version is more commonly studied and more well understood. So we're going to focus on the square one for this video at least. And if you want to see more examples of this extremal function and more explanation, check out the last video where I went over this in some more detail. So first, I wanted to talk about how we can get a pretty simple upper bound on the extremal function using decrease and conquer. So for this upper bound, before I mention it, I want to mention a trivial upper bound that I mentioned in the last video on 0-1 matrices. So for this trivial upper bound, I'll quickly go back to the last slide just to point to the definition. So this EXNP was the maximum possible number of ones in any n by n 0-1 matrix that avoids P. So the most number of ones you could have in any n by n 0-1 matrix, it only has n squared entries. So you can have at most n squared ones. So we can get a trivial upper bound from that, which I'll put on this slide. We can say that in general, EXNP, it always has to be less than or equal to n squared. It also has to be greater than or equal to 0 because you can't have a negative number of ones. And another fact that we mentioned in the last video, you take EXN of the 1 by 1 matrix with a 1 in it, this is equal to 0. So that lower bound can be attained. So this is possible. And this one up here is impossible for fixed P. So this decrease and conquer upper bound that we're going to see, so we have this general upper bound, which is not decrease and conquer. The decrease and conquer one, we're going to take some matrix which avoids P, and we're going to split it in a bunch of smaller submatrices. So suppose that P is our forbidden 0-1 matrix. And here's the claim. The extremal function of Kn comma P is less than or equal to K squared times the extremal function of N comma P. So if you have an upper bound on this one, then it gives you an upper bound on this one, this larger extremal function. Larger in the side length of the matrix avoiding the pattern, not a larger pattern, of course, same pattern. And let's talk about why this is true. And the way that we prove this, it really is a decrease and conquer idea. The visual that you're going to see on this slide, it's going to look like a divide and conquer. But the thing is that the way we divide it up, all of the things that we get are really going to just be the same subproblem. So we'll start with some Kn by Kn 0-1 matrix A, and it'll have the maximum possible number of ones to avoid this pattern P, which is Ex of Kn comma P by definition. So I'm just going to draw a picture of A here. Actually, I'll draw it higher up so it doesn't interfere with our bullets. So here's A. And we're assuming that A is Kn by Kn. And so we'll assume that I'll draw it with like K equals 3 here, I guess. So maybe I'll do a little better drawing on those two. So you got N, 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 N there. That's a K equals 3. And we're going to just take that matrix A, which avoids P, and we're going to split it up the way that I split up in that picture. So we're going to partition it into K squared contiguous n by n submatrices. So contiguous means that these submatrices, they're all in adjacent rows and adjacent columns. So when we look at the picture, the rows in each of these are adjacent, the columns are adjacent. Same with that one, and so on, all 9 of them. So all of their rows and columns are contiguous. All of the submatrices have dimensions n by n. There's k squared of them because we split the rows into k intervals and we split the columns into k intervals to make these submatrices. And most importantly, since our original matrix A avoided P, all of these submatrices also have to avoid P. So we can bound the number of ones in each of the submatrices using the extremal function. So we know since all of them avoid P, all of the submatrices avoid P, and all of the submatrices have dimensions n by n. So that means the number of ones is going to be bounded by EX NP for each submatrix. We have a total of k squared of these submatrices. Each of them has at most EX of NP ones. So each of them has less than or equal to EX of NP ones. There's k squared of them. So the total number of ones in A is less than or equal to k squared times the maximum possible number of ones in any of these submatrices, which is EXNP. And that gives us this upper bound here because we assume that the number of ones in A was exactly EX of Kn comma P. Because recall, A was a Kn by Kn 0-1 matrix. So we can get this inequality pretty easily just by breaking up our matrix A. And it looked like we broke it up into a bunch of different subproblems because we got a bunch of different submatrices. But really, all of these submatrices were the same subproblem. They all reduced to this subproblem because we're just trying to get an upper bound. And we can say that all of these submatrices have an upper bound of EX of NP on the number of ones inside them. So that's a simple example of decrease and conquer for 0-1 matrices. Now, here is a more interesting example, which we actually talked about in the last video. So we fully proved this operation. So we proved that this operation gives the inequality, which I'm about to show. So let me actually get to that. So we'll assume that P is some 0-1 matrix that has a 1 in row R in its last column for some row R. So here's P. 0-1 matrix. It has some stuff happening over here, which I'll denote with a star. And it has a 1 in this last column. It might have other entries like 1s and 0s somewhere, but this in this row R, that's row R. We have a 1 in that row R. And we make a new 0-1 matrix from P, call it P prime. We take P, and we add a new column to it. And the new column only has a single 1 and 0s elsewhere. And for any starting matrix P, which has this 1 in the last column, we can say that the following inequality is true. And we prove this inequality in the last video on 0-1 matrices. So we won't prove it in this one because we already proved it in that previous video. So the inequality, it says, the first part of it is not that interesting. The first part says that the extremal function for P is less than or equal to the extremal function for P prime. And that's immediate because this follows because P prime contains P. And for any 0-1 matrices P prime and P for which P prime contains P, it must be true that EXNP is less than or equal to EX of NP prime. That's a property that we also proved in the last video. And this is the more interesting part. This part actually required a interesting construction to prove. And what it's telling us is that adding this column at the end only increases the extremal function. It only increases EX by at most n. So that extremal function of n comma p, it's only going to go up by at most n when we add that last column. And this gives us a way to prove upper bounds on many different 0-1 matrices using this inequality combined with a decrease and conquer approach. And I wanted to show an example of that. So here's a pretty small example, but this idea that we're doing here can be applied to infinitely many 0-1 matrices. So we'll consider an example where we have what looks like an identity matrix over here. And then we have a bunch of stuff here. Maybe I'll get rid of that last column. I think the idea will be illustrated well enough with this number of columns. So we take this matrix and we want to use this operation to reduce it to a smaller case. So this operation up here, we want to use that down here to reduce this. So we're going to reduce it by cutting off the last column. So we're going to get this first row now of length 7. And we lost that last column. Now we're going to do the same thing. We're going to reduce this one down. We're going to cut off its last column. Now we got 5 zeros. And then we'll cut off that last column. And we just keep on going like this. Cut off that last column. We're getting pretty close to the point where we can use a bound that we already proved in the last video. One more column to cut off. And now we arrive at the 3x3 identity matrix. So we proved, actually, let me say that better. I gave you a problem in the last video. The problem that I gave you was to prove that EXN of, well, we can just apply it for the 3x3. So let's say it for the 3x3. So this one is less than or equal to 2 times 3 minus 1 times n. In general, the k by k identity, the problem I gave you in the last video, is to prove that this one, for the k by k identity, is less than or equal to 2 times k minus 1 times n. So in the case of 3x3, we're talking about 2 times 2 times n, so less than or equal to 4n here. So the upper bound we have for this one is 4n, and this gives us a way to get an upper bound for all these ones before it up to the original. So we got 5n upper bound for that because at most plus n each time. Got 6n here. Got 7n here. 8n here. And 9n there. So we can say that the extremal function for this one right here, so maybe I'll write this at the end, try to fit it there. The extremal function of that one that we drew, I think it's 7 of them. 7 zeros. Whoops. Okay, and then 6 ones in that last row. Yep. And we just showed that it's less than or equal to 9n using this fact, which was a problem that I left here in the last video. But this problem, you can prove that problem using the operations we talked about in the last video. There's multiple ways to prove it. And it's not really that exciting that we got the coefficient of 9. So the coefficient, it doesn't really matter that much. What's interesting here is that we have EX and I3, the 3 by 3 identity. That's big O of n. And this one right here is also big O of n. So anything that we get from an identity matrix by adding on a tail of ones like this, we basically took the identity matrix and we gave it a tail of ones on the right. So adding that tail, it doesn't change the order of the extremal function. So this extremal function for the identity matrix is on the order of n. It's linear in n. And this one, this larger one that has the tail that we added to the identity matrix, it's also on the order of n. So EX for that example, still on the order of n. And that's why these kind of operations are interesting, because they don't change the order of the extremal function. So if you have a very complicated pattern, sometimes you can use these operations to reduce it to a much simpler pattern where you might already know a bound on the extremal function for that simpler one. And then you can show that the more complicated one has a bound on the same order as the bound for the simpler one, assuming that the bound that you have on the simpler one is an upper bound. So here is a problem for you. And this problem, it really is a decrease and conquer problem. So you can use decrease and conquer to reduce this to a forbidden 0-1 matrix that we talked about in the last video. And there's multiple ways to do this reduction. So here's a matrix I'm going to define, LK. It's going to be a k by k 0-1 matrix with all ones in its first column and first row and zeros elsewhere. So let me draw some examples of it just to make sure it's clear. So L2 is going to have all ones in its first column and first row, zeros elsewhere. So there it is. L3, all ones in the first row, first column, zeros elsewhere. And I think that's clear enough, hopefully. So that's our LK matrices. K by K, all ones in the first row and first column and zeros elsewhere. So here's what I'm asking you to prove or disprove. Prove or disprove these bounds. K minus 1 times n is less than or equal to EX of n LK, which is less than or equal to 2 times k minus 1 times n. So see if it's possible to prove that, or if it's not, see if you can find some counterexample. So if you can construct some n by n matrix for some n, which is greater than or equal to k, which contradicts this inequality. So before we finish this video, I want to discuss another operation that you can do on 0-1 matrices, which preserves the order of their extremal function. And this operation is one that allows us to add rows and columns of zeros. So you can take a 0-1 matrix, you can put any number of rows or columns of zeros in it, and it only changes the extremal function by at most a constant factor. So it preserves the order of the extremal function. So we'll say that P prime is a 0-1 matrix with no two consecutive columns or rows of all zeros. So for example, here's a possible P prime that we could have. So example, P prime could be this one. Let me actually make it a little taller. So let's look at this one. So this one, we have a column of zeros here and a column of zeros here. We have a row of zeros here and we have a row of zeros there. Those are the only columns of zeros and only rows of zeros. All the other columns and rows have at least a single one. And this one has no two consecutive columns of zeros and no two consecutive rows of all zeros. So this one is fine. This is definitely a valid P prime. On the other hand, let's say we had some matrix, which is like this. This one is a problem because we have two consecutive columns of all zeros. So that one would be bad. We don't want something like that. So now that we have these examples to illustrate that, I'm going to clear them. I'm just going to emphasize here, no two consecutive columns, rows of zeros. So it's fine to have a column or row of zeros, but it can't be two consecutive columns or rows of zeros. And if we had three consecutive, that would include two consecutive. So if we had something like this, 0, 0, 0, 0, 0, 0, 0, 0, 0, that's also bad. Can't have anything more than one consecutive. Because if you have three consecutive, then you also have two consecutive. So it includes three consecutive, it includes four consecutive. Can't have any of those. You can only have one consecutive. So P prime is this 0-1 matrix, which might have some columns, rows of zeros, but it doesn't have two consecutive columns, rows of zeros. It only has at most a single consecutive one. And it might have multiple of them, but those multiples cannot be consecutive. They have to be spaced out. P is going to be the 0-1 matrix obtained from P prime by just removing any rows, columns of all zeros. So for example, let's say we have this one here. If that's our P prime, then we get P by removing any columns or rows of all zeros. So the P that we get and that's it. Yep. So it's just those remaining entries we have that we did not remove. So the claim here is that the extremal function of P prime is big O of the extremal function of P plus N. And this holds for any P prime, which is a 0-1 matrix with no two consecutive columns or rows of all zeros. So any such P prime, this inequality must hold for it. And we're going to prove that. And in order to prove this, we're going to use this notation, this shorthand. It's just going to save some space. W of M for any 0-1 matrix M is going to be the number of ones in the matrix. So we're going to suppose that A is an n by n 0-1 matrix that avoids P prime, and we'll assume that A has the maximum possible number of ones in any n by n 0-1 matrix that can avoid P prime, which by definition is the extremal function of n comma P prime. Now, first thing that we're going to do to A, I'll draw a picture of this. So we have the A here. And then we're going to turn this into B. And the difference with A and B is going to be that we take the first and last row. Oh, whoops. We take the first and last row and column and make them all zeros. So whatever the entries were before, doesn't matter. They all become zeros in the first row and first column and last row and last column. So all of these are zeros. Now, this might decrease the number of ones. So we had A up here, and the weight of A was EX of NP prime. And our number of ones went down, but it didn't go down by that much. It only went down by at most 4n because there's only at most n ones in the first row. Also at most n ones in that last row. And we have at most n ones in this first column. And we have at most n ones in this last column. These are the ones that we have to turn to zeros. So the number of ones only went down by at most 4n. And we can write this as an inequality. We can say that the weight of B, so that W stands for weight because it makes sense. The number of ones is a good thing to call the weight of the matrix, and the zeros weigh nothing. They're just emptiness. So the weight of B is greater than or equal to the weight of A minus 4n. So the weight only went down by at most 4n. And it's because we only did anything to the first and last row and first and last column, and each of them has exactly n entries, but there's some overlap with their entries. So now I should erase a little, or maybe I can actually translate that. I'm going to move that, I guess here. This looks all right. Okay. So for each A and B, which are between 0 and 1 inclusive, so the possibilities for A and B, there's not that many of them. It's 0, 0, 0, 1, 1, 0, and 1, 1, a total of 4 possibilities. We will let B sub A be the matrix obtained from B, this B right here, by changing all ones to zeros in B, except those with row and column indices I and J satisfying I mod 2 equals A and J mod 2 equals B. So taking that matrix B up there, I'm going to just draw B as a square right here. So we have B, let's just say this square right here is B. I'll put some like scribble in it. There we go. Now if we want to get B sub 1, 1, let's say, and we'll assume that the column numbers and row numbers start at 1. So it's like 1, 2 up to n. So column numbers 1, 2 up to n, 1, 2 up to n. Same on this one, 1, 2 up to n. Okay. So B11, if we take that picture of the B matrix we have over there, to get the B11, we're going to keep this column as is, then keep the third column as is, keep the fifth column as is, and the seventh column as is. And then the rest of it, we're going to turn 0. Well, that's not working so well, so I guess I'll undo that. That looks bad. And I'll use the eraser instead. Okay. So you can see what happened here. These columns, actually, I wrote that backwards. We'll say that this one, instead of B11, is B00, because the way I drew it was actually just B00. So B00, the even columns are the ones we don't turn 0. So the columns, the exceptions to the ones that we turn 0 are the columns with row and column indices satisfying I mod 2 equals A and J mod 2 equals B. So these are the, when we're doing B00, these are the even column and row indices. So we take the even columns and we take the even rows. Okay. And we're going to erase anything in the odd rows. So right here, I'll put back the part that was here though. There we go. And then another odd row we have down here. Whoops. Okay. And then this other odd row was already blank, I think. And this is fine now. Yeah. So the only columns and rows where we have any ones, everything else has been zeroed out. So we can just think of all zeros elsewhere. Everything got zeroed out except for the entries in the even rows and even columns that were ones. So we just would fill the rest of those with zeros. We can also consider what the B11 matrix would look like. So B11, if we just draw the columns and rows that would be in it, the ones that would not get zeroed out. So for B11, the ones that will get zeroed, I'll put the zeros in them. So we'd zero out any of the even columns. So the B11 was the opposite of the B00. The B00, we zeroed out the odd columns and we left any ones in the even columns as I did right there. The B11, we zeroed out the even columns. We leave any ones that are already there in the odd columns. So I'll throw some in there. And columns and rows. So we're zeroing out in the B11, we're zeroing out both the even columns and the even rows. And in B00, we're zeroing out the odd columns and the odd rows. So these pictures are just to illustrate the BAB matrices. And I guess I'll erase them now so we can see the last bullet. So these BAB matrices, we obtain them by turning some of the ones to zeros in some of the columns. And we can see that all of the ones in our matrix B are in at least one of the BAB matrices. And in fact, they're in exactly one of the BAB matrices. So any entry in our matrix B, it's going to be in only one of the BAB matrices, because whatever that entry is, the parity of its indices is going to only have one value. It's either going to be even and even, even and odd, odd and even, or odd and odd. And whatever that pair is, it's going to tell us which of these BAB matrices that the one goes into. So this tells us that the total number of ones in B is the same as the total number of ones in the BAB matrices summed up. So these BAB matrices, they partition the ones of B into four matrices. So we can say the weight of B is the sum of the weights of the BAB matrices. And most importantly, we can use the fact that B contains BAB for each A and B, and A contains B. So we obtained B from A just by turning some ones to zeros. We obtained BAB from B just by turning some ones to zeros. So A contains B, B contains B of AB, which means A contains B of AB. And since A avoids P prime, that means that the BAB right here, I claim that BAB must avoid P. And this is for all A and B. So we can take one of those BAB matrices. Let's just say this is one of the BABs. And we can split this one up like we did the other ones. And we'll say, here's our 0 rows. And then there are 0 columns. So this is just an arbitrary BAB. There's 3 others I could have chosen. So this one would specifically be B of 1 and 0. No, backwards actually. That would be B of 0, 1. Because B of 0, 1, we turn everything to zeros except the row and column indices satisfying. The row mod 2 is 0. So even rows, we do not zero them out. And the column mod 2 equals 1. So the odd columns we didn't zero out. And I claim that this BAB must avoid P. Remember, P was obtained from P prime by removing any rows or columns of all zeros. And why is this? Well, we can assume that if B of AB, if it did contain P, so we had some copy of P in this BAB right here, copy of P in there. That copy of P, it has to be on rows and columns that were not zeroed. So any copy of P in that BAB matrix, it has to be on non-zero rows and columns. And that's because this P right here, it was obtained from P prime by removing any rows or columns of all zeros. So P does not have any rows or columns of all zeros. So the copy of P, it has to be on non-zero rows and columns of the BAB matrix if BAB did have a copy of P. And since it's on the non-zero rows and columns, we can use the zero row and columns to make P prime. So we take the copy of P on the non-zero rows and columns in BAB, and we know there have to be 0 columns and 0 rows between the non-zero rows and the non-zero columns. So that gives us a copy of P prime. And there's one other thing to mention. So remember the matrix B. We obtain the matrix B by changing the ones in the first and last row and column of A to zeros. So this BAB matrix, we're guaranteed to have all zeros in the first row and column. So it's guaranteed. So the way I drew it around that, it's not necessarily going to be drawn like that, but I'll just put a note here. The first and last row and column are all zeros in B sub AB. And that's because B sub AB is a submatrix of B, and we obtain B by turning all the ones in the last and first row and column of A to zeros. So B has all zeros in the first and last row and column. So does B sub AB. So if we have a copy of P in B sub AB, that gives us a copy of P prime in A. So it doesn't necessarily give us a copy of P prime in B, but it gives us a copy of P prime in A because we can use the first and last row and column, which are all zeros. All zeros in both B and BAB. So that gives us our copy of P prime by using both the rows and columns of zeros between the non-zero rows and columns in B sub AB. So that's why we chose to zero out every other column and every other row. That gives us a guaranteed empty row and empty column that we can use to form a copy of P prime between all of the non-empty rows and columns. And we also have an extra row, the first row, and extra last row, and we have the first column and last column of A that we turn to all zeros, and we can use those if our matrix P prime. So the matrix P prime, for example, here's one. We might have example of a P prime, which is like this, which has its first column as all zeros, and maybe the last column is all zeros too. And that in that case, this step right here is important, where we zero out the last column and the first column. So we have used the fact that the number of ones in B is equal to the sum of the number of ones in the BABs. We also need to use the fact that the weight of B is at least the weight of A minus 4n, and all of these matrices BAB avoid P. And each of these matrices BAB, they are n by n matrices. So we can say then that the extremal function of n comma p prime, by definition of the matrix A, we assumed it had weight of A equal to that extremal function. So this is equal to weight of A right here, which is less than or equal to the weight of B plus 4n by this inequality right here. And the weight of B, using this right here, it's less than or equal to 4 times the extremal function of n comma p plus 4n. That's because the weight of each BAB is less than or equal to EX of NP. And that's because BAB, it's an n by n 0, 1 matrix, and it avoids P. So we just substituted there. And for extremal function of NP plus 4n, this is big O of EXNP plus n. So that completes the proof of this bound. And before we finish the video, I want to give you a practice problem, which is kind of similar to this proof. So suppose we have this 0, 1 matrix P prime, and it has no 3 consecutive columns, rows of all zeros. So, for example, P prime, this one right here, that's fine. There's no 3. There's 2 consecutive ones, that's fine, but there's no 3. If we have P prime up here, that one doesn't work because it has 3 consecutive columns of all zeros. Again, we'll let P be obtained from P prime by removing any rows or columns of all zeros. And here's a problem for you to think about. Prove that the extremal function of NP prime is equal to big O of EXNP plus n for all such P and P prime. So this is basically the same inequality you saw on the last slide, except now, instead of a matrix with no 2 consecutive columns, rows of all zeros, now it's 3. So it's 3 instead of 2. So can you see a way to modify the proof that we used on the last slide to prove this result? Or a different way to prove it is fine too. Thanks for watching.